Hello and welcome to Lecture 11 on Special Relativity. In today's class, we're going to see the stunning implications of relativity for how energy and momentum transform from one reference frame to another. We'll also talk about how electromagnetic fields transform from one reference frame to another, and ultimately, how Newton's laws are incompatible with the laws of special relativity and have to be modified, whereas Maxwell's equations are seen to be compatible with the laws of special relativity. So here's the plan for today. We'll start by talking about how the mass of particles and the charge of particles can be thought of as four scalars. That is, these are absolute quantities which all inertial observers agree upon, as in the same way that they agree upon the lengths of space-time intervals. Then we'll rederive the four-velocity transformation law in a more interesting way, which seems a lot more natural. Once we do this, we will understand how to modify Newton's laws to make it consistent with Lorentz transformations. Then we will see that just as in Newton's laws, which are compatible with Galilean relativity, we have a concept of energy and momentum conservation. We now have a more generalized version of energy-momentum conservation in the absence of external forces in special relativity as well. However, one of the stunning implications that we'll see is that even particles which do not have kinetic energy in a particular reference frame still can have an associated rest mass energy. So this leads to the famous equation, probably the most famous equation in physics, E is equal to mc square, which just tells us that mass is a form of energy. So we'll discuss some implications of this result when we get to this section. And finally, we'll talk about Maxwell's equations, and we will show how they are compatible with Lorentz transformation. So the first thing we'll discuss is how mass and charge can be thought of as four scalars. So as we've seen, in the rest frame of a clock, the time that elapses on this clock, on an inertial clock, can be thought of as what is called proper time. And this proper time is a Lorentz invariant quantity. That is, every single observer will agree on the value of proper time. They may have different ways of calculating it, but they will always agree on the value of proper time. So if we draw, for example, the space-time diagram of this clock is sitting at x is equal to 0, and in its own rest frame, some time tau ticks on this clock. In a different reference frame, both these space-time points would have different coordinates, but the space-time interval between these 2 points would still be the same, and or every observer would get the same value of that space-time interval, and therefore they would infer the same value of proper time. Similarly, we've seen that if we have a rod which is placed which is at rest in a particular reference frame, and it has a length L in this rest frame, different observers would measure different lengths for this rod. However, they would agree on what is called the proper length of the rod, or the length of the rod in its rest frame. And the way they would do that is they would measure the coordinates of these space-time points, which appear to be simultaneous in the rest frame of the rod, and they would calculate the space-time interval between those 2 points, and that would allow them to infer the proper length. So they would calculate the proper length in a different way than an observer in the rest frame of the rod, but they would all agree on what the proper length is and what the proper time is. So now similarly, we postulate now that is, we cannot derive this, but we assume this to be true, that mass, or what is called rest mass of a particle, is a Lorentz invariant quantity. And charge of a particle in its rest frame is a Lorentz invariant quantity. Okay, these seem like very natural things to assume that every observer, every inertial observer, would agree on what the mass of a particle is, and every inertial observer would agree on what the charge of a particle is in its rest frame. They would have different ways of measuring this rest mass and rest charge, but all observers should agree on the value of this rest mass and rest charge of a particle. Okay, this is our postulate. So let's denote the rest mass of a particle as m, or m naught, and the charge as E or E naught. Okay, so we might switch notations and just write the mass as m and the charge as E. What we mean by this is, of course, the rest mass of the particle, or the mass in its rest frame and the charge in its rest frame. This is the only thing which we assume to be Lorentz invariant. Now, the next thing we'll do is rederive the four-velocity transformation law. Now, previously, we talked about how if we have a reference frame S with, let's say, axes X and Y, and we have a different reference frame S prime, which is moving with respect to the reference frame S. And suppose we have a particle which we observe in both reference frames, and in reference frame S, this particle has a velocity u, with magnitude u and components ux and let's say uy. So ux is parallel to the direction of relative motion between S and S prime, and uy is perpendicular to the direction of relative motion between S and S prime. Now we saw that there's a complicated rule for how observer S prime would describe the velocities of the velocity of the same particle, that is how they would describe, let's say, u prime x and u prime y. However, when we rearranged velocities in a particular combination, that is, if we took the combinations c over square root of 1 minus u squared by c squared, ux over square root of 1 minus u squared by c squared, uy over square root of 1 minus u squared by c squared, and uz over the square root of 1 minus u squared by c squared, we saw that this collection of four objects transforms like a four vector. That is, it can be related to the corresponding quantities in frame S prime by a Lorentz transformation matrix lambda, which depends on the speed v, okay, or beta, which is v by c. Now, the way we constructed this was rather ad hoc. We sort of guessed that these are the quantities that we have to arrange. But is there a natural way which would guide us towards this guess? Okay, and that's what we're going to look at next. So the way we start is is by thinking about the displacement of a particle rather than its velocity. So suppose in a frame S, it's at location x alpha. So this is its space-time point. And now I denote it as a 4 vector with index notation. So x0 would give me ct, x1 would give me its x coordinate, x2 would give me its y coordinate, and x3 would give me its z coordinate at time t. And let's denote its new spacetime position as x alpha plus dx alpha. So dx alpha is the displacement in its spacetime coordinate. So that is a time dt later. We want to know what is the change in time at which we're measuring its new coordinate, the change in its spatial position, and the change in its dx, dy, and dz. Its change in its x, y, and z coordinates. And one thing should be obvious is that dx alpha is the difference in the space-time 4 vectors of its new space-time coordinate and its old space-time coordinate. So dx alpha transforms like a 4 vector. Okay, so suppose I denoted this as x alpha and y alpha. Both are 4 vectors, and therefore y alpha minus x alpha is also a 4 vector, and that difference is what we're denoting as dx alpha. So this should transform as a 4 vector. Okay, so in general, anything with one free Lorentz index, upper, transforms as a contravariant 4 vector. And now we could also ask, in the rest frame of this particle, okay, in the rest frame of this particle, what is the proper time that elapses? Okay, so the proper time d tau that elapses between these two space-time points is a Lorentz invariant quantity. Elapses in the rest frame of the particle. This is a Lorentz invariant quantity or a 4 scalar. And now if we construct the quantity dx alpha by d tau, dx alpha transforms like a 4 vector, d tau transforms like a 4 scalar, and therefore this entire quantity should transform as a 4 vector, right? The transformation of d tau is trivial, it doesn't change, and therefore the entire quantity transforms as a 4 vector. So what that means is, if I calculate this in frame S, the corresponding quantity in frame S prime, which would be its displacement 4 vector in the frame S prime divided by d tau, and d tau is the same, it doesn't change. This quantity, I mean, I can denote it as d tau prime, but d tau prime is the same as d tau. This quantity would be related to our old quantity. So let's just remove this prime as dx prime alpha d tau is related just by by a Lorentz transformation to the 4 vector in the frame S. Okay, so this is the dictionary for transformation of this quantity, and this entire quantity is what we call a 4 velocity. And we'll see that this 4 velocity is related to the thing we had defined earlier in this sort of ad hoc manner. Okay, So let's work out what this 4 vector is. It's dx alpha d tau, and d tau square is the space-time interval that elapses on a clock which is at rest with this particle in any reference frame, as measured in any reference frame. Okay, so in particular in reference frame S, we can calculate this as c square dx0 square minus dx1 square minus dx2 square minus dx3 square. That is, we calculate the space-time interval between these 2 points. Okay, and that would give us the proper time that has elapsed on this clock. And similarly, in frame S prime, we could calculate this as c square dx0 prime square minus dx1 prime square minus dx2 prime square minus dx3 prime square. Okay. So now let's write out the different components. Let's write down, let's just work out d tau in frame S. Okay, a similar result will hold in frame S prime. So d tau in the frame S would be square root of, it's a positive time that would have elapsed if we look at a time in the future. And so we would have c square dx0 square and now what we can do is we can write this as c dt, where I've identified dx0 as dt, into the square root of 1 minus dx by dt square minus dy by dt square minus dz by dt square. And this is nothing but 1 minus, each of these terms is divided by c square. I pulled out the c square. So this is nothing but 1 minus u square by c square, where ux is dx by dt, that is, it's the speed as measured along the x direction, uy is dy by dt, and uz is dz by dt, or these are the components of what we traditionally call 3 velocity. And so now the 4 velocity vector u alpha, which is dx alpha by dt, okay, can now be written, so if we look at the components, u0 is d dt by d tau, which will just be 1 over the square root of 1 minus u square by c square. And similarly, u1 would be dx by d tau, which would be 1 by c into the square root of 1 minus u square by c square. Let me write it this way. So there's a dx here, and d tau contributes a factor of c dt, so I'll write that here. And dx by dt again is ux. Okay, so I get c. Okay, and so this would be ux prime, or u1. And similarly, I can write down u2 as uy over c into square root of 1 minus u square by c square, and u3 as uz over c into the square root of 1 minus u square by c square. Okay, so now so I can write down now the components of u alpha as 1 over the square root of 1 minus u square by c square, ux by c over square root of 1 minus u square by c square, uy by c, and uz by c over the square root of 1 minus u square by c square. Actually, if I was a little more careful, the way I define d tau is not exactly like this. I would have put a factor of c here, and actually c square d tau square is defined this way. And so the factor of c would drop out everywhere in the denominators. So over here in the numerator, I would still have factors of c. So I would have a factor of c in the numerator here. And I would not have this factor of c in the denominator here, or here, or here, or here. So doing this a little more carefully now, we have a factor of c here, and we don't have factors of c in these denominators. Okay, so this gives us our 4 velocity 4 vector, and this we can obviously see from its definition as dx alpha d tau that it must transform as a 4 vector. Okay, so if we define the 4 velocity properly as dx alpha d tau, then it obviously transforms as a 4 vector. Okay. Similarly, we could calculate d square x alpha d tau square, and this is called the 4 velocity. And similarly, this would also transform as a 4 vector, and we call this 4 vector the 4 acceleration. Okay, this also transforms as a 4 vector. And you can relate it to the conventional acceleration, or the 3 acceleration, which would be d square x dt square, d square y dt square, and d square z dt square, that you would measure in a particular reference frame S. But you would also find that this 4 acceleration depends not just on the 3 accelerations, but it also depends on the 3 velocities. Okay, that is, it depends on ux, uy, uz. And this is something to be expected, because when we looked at our transformation laws for 3 accelerations, which were quite complicated, they depended on the components of the 3 velocity vector. Okay, but if you switch over to this 4 acceleration, things become very simple, right? It's much easier to see that this quantity must transform like a 4 vector. So this is d square x d alpha d tau square, or to be more precise, it's du alpha d tau. Since u alpha transforms like a 4 vector, tau is Lorentz invariant, this entire quantity must transform like a 4 vector.